Hello everyone, my name is João Gross. I am the first of four authors of the work A Dynamic Cost Model to Minimize Energy Consumption and Processing Time for IoT Tasks in a Mobile Edge Computing Environment. This work has been published in the event ICZOC 2020. Here is a brief summary of this presentation. First of all, the motivation for this work is being um, based on four pillars: elapsed time, consumed energy, environmental impact, and edge computing technologies. First, elapsed time. We see that, for example, Amazon Web Services delivers around 100 milliseconds of latency to South American data centers. And we see today a trend for applications such as tactical applications that have requirements of 1 millisecond. So cloud computing is a paradigm that is not appropriate for this kind of scenarios. The second pillar of our motivation is consumed energy. Most IoT devices we see today run on batteries and have energy constraints. And when they process large volumes of data, they require a lot of energy. Also, when we talk about environmental impact, we see that data centers are responsible for a lot of the CO2 emissions in our world today. And CO2 is the main greenhouse gas emitted by human activities. So if we can reduce the CO2 footprint, it will be a good impact for our climate and reducing some climate changes that we are seeing nowadays. And finally, the fourth pillar of our motivation are the edge computing technologies, especially mobile edge computing that introduces an intermediate computing layer between IoT and cloud devices. It provides cloud resources such as um, processing close to the end user. And this technology, this mobile edge computing layer, is focused on mobile networks. That is an enabler of the 5G era. And it's good because it Mac can preserve the battery level of the mobile devices and helps to reduce the response times of applications. The objectives of this work are to minimize the energy consumption, the overall and consumption of the system, and the elapsed times, that is, processing times and transmission time. Our model is a three-layered architecture. The first one in the bottom are the IoT devices that are the end user devices. They interact directly with the Mac layer, and the Mac layer interacts directly with the CC layer. Each layer has a computing power, and the intermediary and top layers require data transmissions to offload the task that has been created by the device in the user device. So if a task is going to be offloaded to the MAC or CCE layer, it has some hops of communication that are considered in our model that consume energy and time. Our cost model is divided in two equations. The first one is a cost per task. That is, we compute the costs of each layer for the respective task. So we take a task I, and we see the costs for the local layer, the MAC layer, and the cloud layer. The minimum cost is chosen, and the task is offloaded to the corresponding layer. If the task E is kept on the device itself, no offloading is done because the task is already on the device. Finally, we have the system costs equation that computes the sum of all the costs of each individual task. So we have all the costs of the tasks in the system costs. We developed an scheduling algorithm to analyze the resources that are available in the system and to perform the allocations of the tasks. So in this algorithm, in the first step, the algorithm collects information about the CPUs that are available, number of CPUs, battery level of IoT devices, and available wireless communication channels, and also the task set. In step 2, we define processing places, first allocating critical tasks that have a deadline, and then regular tasks. Step 3, we check the conclusion of tasks and update the available resources. In step 4, we check for new tasks and update the battery level of IoT devices. If tasks are still running, we go back to step 2 and keep doing this cycle until all tasks are concluded. We develop a simulator to execute our experiments. So the simulated was configured in a Mac environment with IoT devices and connection to the cloud. In these experiments, we used the TMS scheduler. Our simulated network was done with Arduinos for IoT devices, Raspberry Pis for Mac servers, and Intel Xeon Cascade Lake for the data center. We ran 7 different testing scenarios and had very good results in these experiments. We saw in these experiments that our model with the TMS algorithm allowed the energy of the system to be reduced by up to about 50%, and the total times to be reduced by around 86%, ending critical tasks before deadline. That is, the tasks were concluded correctly, they were not cancelled. The system has become more sustainable because of the reduced energy costs, and the user experience has not been affected because task has been concluded successfully. Our model has a three-layer architecture altogether in a single architecture that includes MAC and CC services in addition to local IoT computation. And this approach enabled a more detailed cost model, including not only energy and time consumed during processing, but also the cost of the data transmissions. Our model considered costs not accounted for by other models, such as costs with data transmissions, time spent in quiz, and interaction with the cloud. Thank you.